had a very tough time because so none of them would be talking about kinematics and dynamics very explicitly. So for example, one of the textbook which we refer is Roland Stigward. Okay, that book may be one of the standard textbook, but even then the kinematics and dynamics will not be explicitly given there. So then there is another competitor, or you can say the contemporary book is Introduction to Mobile Robot Control. So that book would be talking more on control rather than the kinematics and dynamics. So that's why I thought I can actually like give that idea behind, so that you will get to know like how to get it, all those information. And more or less, so this particular session I will be taking from my, you can say, NPTEL Swayam course lecture material. Please excuse, because I don't have enough time to prepare individual PPT for this particular short-term course. Since it was actually given kinematics and dynamics of mobile robot, I thought, okay, I can use already whatever I prepared for the NPTEL course. So that is what the idea. So I'll be actually skipping few lecture numbers. So please don't mistake that. So those lectures are actually like either probably simulations, or probably it would be slightly different from build the mobile robot. That's what the overall idea. So let me actually like first justify how I would be actually like suitable to talk this. So I was actually like joined as a faculty probably in 2012, but I was actually like involved in mobile robot since 2000, where I was in second year BTech. I got one of the internship project, and then from then I was working on wheeled mobile robot. And I traveled Japan and Korea during my student life. So then after that, I traveled at least 5 European countries, and you can see I have an exchange of, you can say, different countries for this particular aspect of research. So in the sense, I have seen a little bit on wheeled mobile robot worldwide. I thought I can share few of my experience to you. I'm not actually like old enough to give all the comment, but definitely with my small little experience can give probably a motivational aspect of you. Okay, because it's a faculty development program. Because I don't know like whether everyone is interested in robotics, but some of you might have just want to know. Definitely, I will try to trigger it something for you. Okay, that is what the overall idea. And if you want to know more about, you can say, the NPTEL course and all, I already shared the link. You can go across. So let me actually like start the formally introducing this course. So this particular course would be having, you can say, my content. In addition to that, I would be using some of the web pages or books. Anyhow, I am not going to share any videos, because since it is actually like given into NPTEL, so obviously the videos I need to get copyright, and also I have not given any videos. So in that sense, even in this lecture also, I will not be showing any videos. But some of the material I would be using from the other resources. So I will not be giving directly cited there, because that is actually like a long lecture. I cannot give every aspect. That's why I'm just giving this disclaimer. Okay. So with that, let me actually like go. So the first session I'll be talking about kinematics of, you call, mobile robot. So for that, first I need to define what is mobile robot, then why we need to actually like have the kinematic relation for the mobile robot. Then we can actually like see why we need to go for dynamics. So this is what the phase. So for that, I will actually like start talking about basic definition of robot. Then I'll be defining the mobile robot. Then we will go with the kinematics, and I'll be ending with why we need dynamics. So these are the cases. So let's start with what you call robot. So robot definition, you would have got it probably last 3 days different way. So I'll be giving definition is slightly different. Any robot I call effector. So what that means, so any robot or robotic device that has an effect on the environment, that is what I'm going to call as effector. Okay, so effector is nothing but robot or robotic device. So now you can actually like look at it. This effect on the environment can cause, you can say, majorly 2 different motions. So the effect on the environment causes motion of the effector itself. So what that called, that is called locomotion. For example, simply you take a football. Okay, on top of the football you are standing and you are actually like trying to roll the ball. What happens? The ball will roll, and if you are actually like able to stable, what you will get, you will also like move along with the ball, right? So the other case, so the effect on the environment, you can say causes motions objects around. Now you are not standing on the ball, but you are actually like seeing the ball in front and your leg is actually like trying to maneuver. Okay, in the sense try to manipulate that ball. So based on that, you would have two different classification. So one classification what we are going to cover in this particular course, which is nothing but a locomotive device. So if the effect on the environment causes motion of the effector itself, this is what we call mobile robot. Whereas the other one, if the effect on the environment causes motion of the objects around, that is what we call manipulating device, simply we call manipulator. Since manipulator means usually we take it as a mechanical means. So since it is a robot, so we call robotic manipulator. Okay. So I hope yesterday my friend Sudhir has covered kinematics and dynamics of robotic manipulator. So you would have actually got more information about robotic manipulator, but I would be talking more information about the mobile robot. Just to give a small idea how the locomotion happen, you imagine you take a wheeled mobile robot. So now the effect, so where it is going to create, so the wheel would be actually like touching the ground, the wheel is actually like hitting the ground, and then because of that you are going to get a traction force. That traction force push the vehicle whatever way you want. So now based on that what we bringing, so the locomotion is actually like bringing as a major case, which is nothing but mobile robot, and the other one is actually like manipulation, so that is actually like sub cases. So you know, like robots are not actually like new. It started from 70s. In fact, you can say late 60s it started, but early 70s it was picked, and you can say mid 80s it was set some kind of saturation. In the sense it is actually like stable improvement, and 90s it is actually like ruled most of the industries, and 2000 onwards even actually like the case moved. What case moved? So initially robot means we all assume that it is manipulator arm. But now, if you call robot, then we expect that robot would be having mobility. So this is what the difference. That's why I clearly said that that is robotic manipulator, not robot. Okay. So this is the basic difference. So in that sense, you can see one will give, you can say maneuverability, the other will give manipulability. These two are the two sub cases. So now obviously you will know that. So one additional case which I'm going to cover in the next session called motion control or control. So then what would be the role of control? So several of people call controller also one of the effector. Certain extent I do agree, but the controller is not supposed to be called as an effector, because it is actually like trying to make sure the effector is giving the desired effect on the environment. So in that sense, the controller is actually like aiding tool, not as a effector. That is what the overall picture. In the sense, if I call robot can be called as effector. So in that locomotive device and the controller all included as a single entity called effector. That's what I want to maintain as a, you can say some kind of trade-off here. So let us actually like go further. So you know, like already you have seen last day what is manipulator. The manipulator, you know already, it is one side is actually like fixed. Okay, it is actually like serial manipulator or parallel manipulator. Definitely one end is fixed. That end, if it is actually like put it on a mobile base, then that is a mobile manipulation. But you imagine it, if it is a manipulator, it is nothing but a fixed manipulator. If it is a fixed manipulator, what you can see, the end, if it is actually like parallel manipulator, the mobile platform, if it is actually like serial manipulator, the end effector would be having a reachability within certain constrained way. So in the sense what you can see, the manipulator will work in, you can say constrained workspace. Because of the constrained workspace, what you can see, you can say perceiving the world around them is need not to be necessary. You put a fence, then also like a manipulator can work. Further, what you got idea, like because most of the manipulator has a joints, so those joints easily you can actually like estimate the absolute measurement. So in the sense, for example, you take a rotary joint, the rotary joint you can use as a encoder, or you can use as a probably potentiometer. You can get the absolute measurement of position easily. Whereas if you come across the other side, which is the contemporary of manipulator, so definitely you can see it is not operating in a constrained workspace. It is definitely unconstrained. Even certain extent, the unconstrained workspace is something like unstructured. What that means? For example, now you put the mobile robot within the room is probably structured. Now imagine the mobile robot you are putting on the field. For example, you are putting in a war field or forest, so which is completely unstructured, right? So in that sense, what you need to know, two things. One is you should know what is actually like world around the mobile robot. The second thing is you should understand where you are, right? The exact position of you, the sense mobile robot, and as well as what surround the mobile robot, both are supposed to be required. So these all actually like you can say some kind of difference between these two. And further what happened, the sensors which are used in mobile robot are actually like some kind of tricky. So that we will see in later slide. So now then people will think one of the easiest way, okay, this is having some pros and this is also having some pros. Can I actually get a dual advantage by, you can say, combining? What that means? I take this mobile, or you can say this manipulator, put it on the mobile robot. So which is what we call mobile manipulation. So definitely that is going to give a dual advantage, what I already mentioned. So it will give both maneuverability and as well as manipulability. In addition to that, what you get, so the mobile base offers unlimited workspace to the manipulator. In that sense, you have actually like abundant workspace for the manipulator, which is actually like one of the critical case, which is actually like one of the easiest way to understand. And most of the mobile manipulator systems are actually like manual. Very simple example you would have seen on the roadside where the earth movers, in specific the backhoe, or you can say excavators and all. These are actually like one of the, you can say, bigger vehicle manipulator system, which we call mobile manipulator system. But in the current community, so the mobile manipulator is actually like playing a major role. How it is, that we will see in upcoming slides. So for understanding that, you can say the mobile manipulator role, I'm just giving a basic idea. Okay, I already said late 60s and early 70s the robotics started, right? Or robot system development started. Since then, people are working into broader thing. One is actually like try to increase the human life, or you can say humanity's aspect. The other side is actually like try to, you can say, enhance the machine's capability indirectly, try to increase the productivity. One is actually like probably profit oriented. The other one is actually like benefit oriented. So both you can put benefit oriented, but I said one is part about, you can say, talk about humanity, where the money is not the concern. You are trying to increase the human life. The other side is actually like you need to make optimization and try to make sure that whatever you are implementing, that profit oriented. So your resources is actually like maximum utilization. You know, like engineer itself is actually like one such case. So what that means, when the engineering started, if you recall, you can see like in the Stone Age or probably even before, you can actually like imagine. So when the people are actually like starving, in the sense they are hungry, they try to actually like do something. For example, you want to cut a tree or you want to actually like kill an animal, you cannot actually like do it with a rounded surface, right? So what people did, so they tried to increase the efficiency of the effort what they are providing in order to like sharpen the tool. So there the engineering has started. So you see the basic engineering, I'm giving my own perspective. Even the basic engineering where we are talking about the economic benefit or efficiency oriented. So in the sense you can see like both are actually like coming. But why this humanity is important? That is what one such case. For example, several people would be disabled. The disability is actually like need not to be only physical disability. So lots of things are come. So this is one side. In addition to that, in the current scenario, lots of other problems also coming. What lots of other problems? For example, you take, when I was a kid, I was in a joint family. There are 6 or 7 grown-ups always there, and neighbor all are actually like our relatives. So in the sense, you can see like you don't need to bother about your peer group, either elderly people or you can say middle-aged people or the younger one. They don't bother about the peer group. So they have always some company. Whether the company is actually like you can say strange or not, that is different. But you have a company. But now in the current scenario, everything is nuclear, right? So even it is much more stringent, at least which I come across probably like few of my colleagues. So the spouse are actually like working in different, you can say, organizations. So they used to meet once in a week, once in a month, once in a semester, some cases even once in a year. So then you can see like their family attachment is actually like going away. In fact, a few years back, my friend was having actually like his family, this was actually like strange. The kids were there in his hometown. The wife was working in US and he was working in Indore. So they used to meet all together once in a year, that to summer vacation. It was very strange, right? So these all actually like happened. Based on that, what you can expect in upcoming years. So the accompanying person is actually like very important. You definitely need it. So in the world, you can say classical solution is actually like peer group can bring it in terms of pet animals, right? But you know, like most of you are staying in apartment or residential complex. So where the residential complex in the front door itself, they put a sticker, right? Pets are not allowed. So whether you are a owner or tenant, you have no rights to have a pet animal. So then how will you fulfill the peer group, you can say, limitations? So then you can see like some kind of aspect will come. So that is what we are actually like seeing one side, the humanity oriented, we call companion robot or assistive robot, these all. So these are one side human friendly robot. The other side, the industrial work cell, the olden days, or you can say at least 10 years back, the industrial cell is mostly like a fixed layout. Although robots are there, but it is actually more like structured. So this is what the sequence, okay, based on the sequence, the systems would be connected. But now it is no longer exists because the product versions are actually like immediately getting changed, and you need to actually like modify. So in the sense what you need to have a flexible layout. So in the sense what you want a smart autonomous robot, in the sense smart industrial robot. Here autonomous I call actually like small intelligent, not you can say network connected, because most of the smart manufacturing, smart industry means it is actually like IoT or IIoT related. What that means, it is actually like connected in a cloud and you have access in, you can say, remote access. I'm not talking about that smart. So here smart means a little bit autonomous or autonomy. So these are the two broad things. One is actually like for human friendliness. So the other one is actually like flexible layouts. So these two are actually like focus. You can see like most of these applications or the theme end up with something close to what you call either mobile or mobile manipulator, right? The manipulator is actually like really independently not working all the cases. So in the sense you can see like you need to talk about mobile robot and mobile manipulator definitely in upcoming years. In the past probably you would have skipped, but in the upcoming years definitely you need this. So in that sense, what you need to know, how will you choose certain things? For example, I'm saying like I'm giving some application. How will you choose the, you can say, chassis? How will you choose your body? How will you choose your wheel? How will you choose your actuator? How will you choose your sensor? How you arrive the controller? How do you control the, you can say, overall system? How will you design? How will you navigate? How will you actually like maneuver? All those, how that question or what that question will definitely make it. So now in order to make this all, you cannot make a product and then test it directly, not like a Japanese olden days. So olden days in the sense 80, 85 or 90s and all. So the Japanese people, they are actually good in making it. So they make the prototypes, they test it, and based on the test, they actually explore in the sense knowledge base. So they are actually very good in making a system. But if you see in the other side, Western, at least European people, they are slightly different. Now, most of us actually like more to European style. Why? Because this is giving more economic benefit and logic based. For example, you have a system which probably consuming probably 2 lakhs. You cannot make it and test it and the test is failed. You cannot throw it. The Japanese people, maybe olden days, they have done that. But now they are also not doing that way. So in the sense, what you need to know, you need to understand the system behavior and you have to actually like make sure that your proposed system fulfill that or not, at least some kind of thing. So for that, what people used to do, one is mathematically analyze, then virtual prototyping, third one prototyping, fourth only the final, you can say, product implementation. So now you can see like this virtual prototyping and mathematical model are actually like two contemporary areas. So why I say two contemporary areas, for example, I'm in mechanical, so I definitely believe that a mathematical model is actually like very important. But somebody who is from probably IT or CSE or electronics area, they said, I don't want, I will buy the system, or what I will do the virtual prototype. For example, several open resources or probably several packages are there. For example, you take Adam's robot or probably robotic toolbox in MATLAB, or you can say robotic operating system connected with several open source packages like RViz or MoveIt, or probably you can say Gazebo platforms, and all these all actually like definitely helpful to do virtual prototyping. In the sense, the guy or the girl really don't require to mathematically model the system. But when you actually look at it, what that system or what the package is working, that you should know. So it may be actually like false, right? Because it's all open source mostly. So the open source probably I'm making and I'm putting in a cloud, or probably I'm putting in a forum. So you cannot actually like trust I have done everything proper, right? So in the sense, what you need to know what that solver or what that you can say model or virtual prototype is made up of, and how that is actually like justified. In the sense, somehow you are actually like triggering it in one single entity. What that means, so you need to understand the mechanics of robot. Indirectly, I call the physics behind the robotic system. So that's what you have covered in the last two sessions of tomorrow, like yesterday's morning session. Here we are actually like extending that into a mobile robot. So there is a broad difference between, you can say, manipulator and mobile robot. So the manipulator is multi-body. I'm really sorry, some windy noise is coming. Should I talk or have to wait? Okay. So now if you look at it, so the manipulator study, whatever you have studied, is actually like one such a small case. What that means, it is actually like a very, very narrow path. So although you are talking about multi-body dynamics, but you never end up with a multi-body dynamics there. You will go that too, like you would have started talking about serial manipulator. What you would have done, you would have ended up with one single representation that was actually like more, you can say, compressed with several assumptions. The one of the simplest assumption is say that every body would be considered as a binary link, in the sense that body can have only two joints. The second assumption is every joint can connect only two bodies, and only one motion is allowable. The relative motion between two bodies are actually like either translation or rotation. That's all. So now these all actually like restrictions making, you can say, some kind of handicap. When you try to implement the same scenario to mobile robot, it won't work. So then what you need to know, you need to work on, first of all, you have to start with the rigid body. Then you can go interior with multi-body dynamics. So in the sense, you have to talk about vehicle dynamics and you call rigid body dynamics, you can say, close together. But obviously I cannot cover in 3 hours this what you call motion dynamics, vehicle dynamics and all. So then what I can do, I can actually give a small idea, very small idea. So why we required kinematics and dynamics, why most of the, you can say, mobile robot community restricting to what you called kinematic system, kinematic control, kinematic design, why they restrict and why they are not going to dynamics when you want dynamics. These all I would be addressing. Okay. So this when and where, I think you can actually go through in a different slide. So right now what we are actually like seeing it. So we are talking about mobile robot. You all know like mobile robot means it is capable of locomotion. That is what more important. So in other way around, if you put it, it is capability to move around. But I'm not actually like specifically mentioning what kind of mobile robot, because the mobile robot can roll, walk, fly or swim, even anything else can also bring it. But here I am actually like going to focus on the roll. What that means, actually like you are going to have a wheeled mobile robot. But so I'll actually like give most of the, you can say, study in more general to the ground based mobile robot. What that means, on a planar case, the general study of what you call kinematics and dynamics. That is what I'm going to restrict to this particular case. So now you can actually like get an idea what that the remaining or not. Okay. So with that, we will actually like talk about more other aspect. So for understanding this, what are the components we need to know and why that component need to be there in mobile robot. For that, I'm giving a one simple example. Okay, so you assume that I'm a Korean. Don't immediately get a counter attack. So you imagine that I'm a Korean and I'm working in Seoul National University, and I had a partner who's working in IIT Madras, and we have actually like certain, you can say, combined or collective talks and all. So IIT Madras professor decided to organize one workshop, and he is inviting me, and he called me and say that, hey Santhakumar, you have to come to IIT Madras. Your flight ticket, everything I will book, and I have booked already the guest house. And you come down to Chennai airport, there would be one driver who picks up and he will take it to the guest house. And this is the case. So and so day, and this is the way. Still, I'm actually like kind of conservative guy. I just gone through something like, where is IIT Madras, from where actually like I can go, for example, airport to IIT Madras, what are the landmarks. I'm just, as a, you call something like a conservative guy, I'm just getting to know, because I'm not good enough to talk in Tamil or Hindi or English. I can read, but I cannot, you can say, fluently talk to everyone, you imagine, because I am a Korean, right? But I can actually like handle the session, but I may not able to talk in a local way. That is what the limitation. Now what happened, I'm actually like taking a risk. I'm actually like taking a flight from Incheon airport, and I'm coming down to Chennai International Airport. I'm coming out and I'm expecting the driver to show the placard. Somehow, before seeing the driver, so what happens, some of the gundas who actually like assume that, okay, so I'm the guy, so they pick me and blindfold me and put it in the cab, and they take me to the, fortunately, on the road to IIT Madras itself. They are actually going towards Guindy, imagine. Okay, so later on the phone call came that I am not the supposed to, you can say, kidnap somebody else. So they throw me just probably in front of probably Katipara Junction, imagine. Okay, so fortunate that I've seen everything on, you can say, even images. For example, airport metro, what look like, Radisson Blue Hotel, how look like, Katipara Junction, how look like, that I actually like registered on my memory. So now I thrown out of the Katipara Junction when I unfold my blindfold. So what I will try to see, first I will try to localize where I am, right? So how I will do, I will try to map with the landmarks which I have come across, or I will try to see some of the, you can say, direction board or placards or whatever the, you can say, identity is there, that I will try to make sure that where I am, right? So in the sense, what I try to do, I will try to localize. So once I do localization, then what I will see, for example, now I understood that I'm in front of Katipura Junction. Okay, then after that, I have to go to Guindy Junction, then I have to take, you can say, the magistrate, then take turn, then see Anna University, still go further, I can see on the right side Cancer Institute, then you can see Snake Park, then I take, you can say, U-turn, and then I can reach the IIT Madras. I'm happy, right? So then you can see like what I'm trying to do, I'm trying to make several questions and trying to answer. But robot can do that? No, right? So the robot, what it has to do, it has to make the questions, where I am going, and how do I get there. So these questions are definitely putting on the, what you call, mobile robot community, right? Because it's after all a machine. You are actually giving some kind of, you can say, prefixed controller or some kind of intelligence to that. So obviously these questions need to be answered. So how you will answer, definitely you have to make measurements. Making measurement will give what? The model, the environment, understand where you are, then localize yourself, then plan the path towards the goal and control its motion, and finally you will achieve everything. So if you look at these all, so what one can see, so the robotics itself will be having 4 sub, you can say, components. So what those components, you need to have a mechanical body. That mechanical body is supposed to have an actuation system. So that is one of the pillar. Then you need to understand what around and what you are and where you are, all those things. So you need to have some kind of sensing. That sensing is not alone enough. You need to perceive that to an informative one. That information you need to process and use some kind of, you can say, useful form. That is what we call navigation. So now that navigation is actually like very broad. That navigation would be associated with a constraint, associated with something higher level, that is what you call guidance. So guidance is something like on a mission level and constraint level, all your views and the navigation will give only, you can say, certain direction, but this direction would be executed by this. So finally, you can see that the execution done at a lower level. For example, I am taking a mobile robot. I say that you take straight line, just imagine, and say that move forward 10 meters. Who would do that? The motors, right? So where we are coming back to the lower level, right? So in the sense of motion control and the task execution at again happening on the device level. So where the sensing, perception and navigation, simply you call guidance and navigation, these two blocks are happening on top of the device, which I call, it is actually like element layer, which is actually like higher layer, where the lower level is the, you can say, physical structure and the execution part, right? So now you can see, this is, you can take in a simple example with a race car. For doing the race, definitely you should have a car, right? For doing the race, you should have a driver. The driver would be nothing but the motion control guy, because he is going to do the final execution. But for that, you are saying the race track, and you have to say that you have to do so and so things, right? You take left, you have to collide, you have to do this. For example, something happened, you have to go to the pit. So many guidance all will be given. These all would be in one of the green pillar. But in addition to that, you need to have something like additional aid. What are those things? You have to see your camera, you have to see your, you can say, needle, and you have to see left, right, everything. The driver cannot do all alone. So what he used to have are the navigational crew members. So they would see the mission statement, they see who are all coming behind, who are all going forward, what is ahead of you, what happening in front of you, probably accident, then you stop, you have ahead of sharp turn, you reduce your speed. No, somebody is actually like trying to chase you, you increase your speed, all the navigational commands given by someone, right? So in the sense, you can see like even for a race car, you should have this. So similarly, the mobile robot also should have all four pillars. Unfortunately, I am not going to cover entire thing in this particular 2 sessions. What I am trying to cover something related to mechanical design, okay, and I'll be talking about close to a motion control. That is what I'm trying to cover in this particular whole session. Okay, so these all actually like skipped scenario. I'll actually like come back straight away the lecture. Okay, what you need to have. So this particular handout will be talking about mobile robot kinematics. Okay, so you would have actually like already come across what is robot kinematics. I know, right? You have already studied that robot kinematics. So it is still general physics, right? What general physics? Kinematics means study of motion without considering the cause of motion, which we call without regard of forces or moment or the effect which caused the motion, right? This is what you already studied in the last 2 sessions. In addition to that, you would have studied one more thing. What that? Robot kinematics is nothing but kinematics. In addition to that, it is a mapping, right? That's what you would have studied last 2 sessions. What that mapping? So you have 2 different spaces or even n number of spaces. You are trying to map one space to another space in certain domain. For example, if I still clearly says, I think Professor Sudhir would have talked about task space and joint space, right? Where you have 2 sets of variable. That set of variable I call space. So now there is a task space, there is a configuration or joint space. Now you need to map the space in position domain. What you call that is a geometrical model. If you know joint space, you call task space. That is what you call forward kinematics. Similarly, if you know task space and you find it, so this is what you call inverse kinematics. The same way you go one step further. What that means? You go the velocity domain. So earlier you have done a simple geometrical model where you have done everything in a positional domain. So you have gone one step further. What you have seen velocity. So now task space velocity and we call end effector velocities and joint space velocities. You are trying to map. So there also you are using a transformation matrix, right? But what you have done there actually like it is a difference, right? So you are doing a vector difference with respect to another vector. So definitely you cannot do it in a single way. So what you have done something like a partial derivative consists of a matrix consists of partial derivative. That philosophy gave by a Jacobi. So that's why we call Jacobian. This Jacobian is actually like one of the kinematic transformation matrix which maps between two space in a differential domain. Okay, so here we call velocity, but it is a differential domain. So this is what going to happen when we talk about manipulator. But in mobile robot, it is not going to happen that way. Why? That we will see. So for that, we will bring it back the kinematics I already mentioned. It is study of motion without considering the effects that affect the motion. Definitely, that is I agree. But why you need to know the kinematics? Because you need to have a geometrical relationship which govern the overall system behavior, and you need to have a relationship between the control parameter and the behavior of the system in you call state space. It is very, very important, at least in the mobile robot community. Okay, that is what we are trying to see. And similarly, the next slide, which would be talking about why we need mathematical model, you all know. So why we need to understand the system, we need to design the mechanical system, we need to design the controller, we need to design the navigation, we need to design the guidance, we need to actually, like certain cases, we need to estimate or predict the, you can say, certain parameter. So these all actually, like we know, it's a very general aspect for mathematical model. I'm extending that to a you call robotic system also. You all agree. So now when you do the mathematical model, or when you want to understand the overall behavior of the system, so what you have to see, so after all, robot is a motion making system or motion system. So in the sense, what you want to understand how the motion happens, right? So motion happens means what you need to know. You need to talk about what is the positional information, how it is oriented on the, you can say, given space. These all you need to know. So now you need to describe this. So in order to describe, you can actually describe a number of ways. For example, I can describe this bottle probably 1,000 ways or even more than that. But I want to actually describe in such a way that I can uniquely identify this is what bottle. Then you can see like you are bringing down to minimum number. Very simple example. Okay. So you want to actually like somehow the former faculty of IIT Indore visiting your institute. Okay. So you forget about me. Okay. So you don't remember my name on the day, and you are actually like don't remember even my department. Imagine. Okay. So what you are actually like trying to, you can say, give some kind of description to the one who come from the IIT Indore. You want to actually like make sure that he understood so whom you are talking about. So for that, what are the credentials you will give? Hey, he is from robotics. Unfortunately, even now in IIT Indore, nobody is explicitly working on robotics. Imagine, so there are plenty. So this guy could not understand. Then you are saying that he has come from IIT Madras. So in that case, in IIT Indore, probably at least 20 odd faculties are graduated from IIT Madras. So he cannot take it. Then you are saying that he has actually like gone to Germany for a, you can say, year for his sabbatical. Then okay, he may recall because several of them visited Germany. At least I know during my 7 years in IIT Indore, 3 or 4 gone to, you can say, Germany. So definitely he cannot even recall. Then you say that he left the job. Then you see like at least I know 2 of us who come from Germany and left the, you call, IIT Indore. Then you are actually like making further and further. You say that he visited IISc. Then you can see like it is furthermore, he could understand like to whom you are actually like visualized, right? Then he say, oh, Santhakumar, you are talking about Santhakumar. I know him. Oh, yeah, he's friend of mine. Like that he's saying. But now you are giving a minimum number of descriptions so that he can understand me, right? So this is one thing. And second thing is, so now you want to describe in a general way about my physics. You are saying that you are actually like talking about me. He is a short in height, dark in color, probably long hair, or you can say he's talkative, like that. You are actually like telling some description. But this description is actually like not, you can say, as common to everyone, right? The dark in color may not be applicable to, you call, African countries, right? Probably the short in height may not be applicable to Mongolian countries. Long hair may not be applicable to certain countries like France or Italy or no, right? So similarly, talkative is not at all actually like qualitative one. So now if you are actually like saying this, what you are actually like bringing it, you are bringing it two things. One is you are trying to make sure that the minimum number of variable to describe the system, that is what we call degree of freedom. But even then you are actually bringing some reference. So the reference also like important. So in this particular two session, we are going to take a very common reference system, which we call Cartesian coordinate system, which is three mutually perpendicular axes. That is what we are actually consider. So since the Cartesian is given, so we are calling Cartesian coordinate system. Okay. So that is what the overall idea. So now you know degree of freedom means minimum number of variable or number of independent variable to describe the system in unique sense. That although I have not explicitly given, but that is what the case. So if that is the case, land-based wheeled mobile robot or water surface vehicle required only 3 because that is in a plane. So what maximum it can do? It can do 2 translation and 1 orientation. Okay. If the vehicle is actually like on 3-dimensional space, in the sense space or aerial and all, you can see like the degree of freedom is 6, right? So now I think you would have studied the degree of freedom in manipulator as number of controllable axes, but that is not right. So what that means, that is actually like a manipulability. Degree of manipulability is what you have said, that number of controllable axes. The degree of freedom for the robot, if it is in a planar, it is having 3. If it is in a space, it is 6. Your number of controllable input can be 4, 5, 6, 7, even 10. Even number is actually like high. But when you want to describe the system, minimum number required is 6 if it is in 3-dimensional space. Please make it clear, because most of the textbooks would have given robotic manipulator degree of freedom means number of axes. It is not true. Okay. If that is the case, the parallel manipulator number of axes would be more. Then you will say number of controllable input. That is also not true. Okay. This all talk about degree of manipulability, not degree of freedom. Degree of freedom is actually like you need to know what is the minimum number of variable to describe. For example, even you take a planar case, okay, planar case, I assume that it is having probably 10 R joints. So what is the end effector description with respect to the ground or with respect to inertial frame? You need only 3 variables to describe, right? X, Y and psi, which is the Z axis orientation. But although it is connected with the 10 R joint, 10 independent variable can come. But minimum number of variable to describe the overall system required is only 3, right? So in that case, the degree of freedom, you should not say 10. That you should make it clear. That is what the overall idea here. So in that sense, so if you talk about land-based or aerial, the number of controllable input may go further, right? So that we are going to talk as a degree of maneuverability here. So there in the manipulator you call manipulability, but here we call degree of maneuverability. You got clear, right? So this is what we are actually like trying to say. So I already told, right, this is actually like wheeled base. We are bringing the general case. So what the general case, I assume that the blue portion, which is a blue rectangular box, which is on a single plane. Imagine it's a magnetic duster, which is put it on the whiteboard. So now how many degrees it is having? It is having 3, right? The magnetic duster cannot come out until you plug it. So now imagine, so if that is the case, this can have a translation in x-axis, y-axis and z-axis rotation, right? So now it is having 3 degrees. You all agree. Okay. Now I want to describe. Can I do it that? Because this is having multiple points. I cannot even fix a frame. So then what I can do, I have to fix something somewhere in the frame. That is what I need to do. For even describing this, I need to have some reference. That reference I am bringing it on the blackboard or whiteboard itself. One of the corner I am keeping it, that is I am calling I. As I already said, I am going to use a Cartesian coordinate system. So this is what the Cartesian coordinate system. Since it is in a plane, so I can restrict with the x, y, the z would be coming out of the screen. So in the sense, this is I know. Now even then I cannot define this mobile robot as a single entity. Why? Because there are n number of points associated with the blue box. So then what I have to do, I have to make it something. So what easiest, I can take the centroid. So that I fix another frame called body frame. So now you can see that the B is the body fixed frame, which is a mobile frame, and where this I is earth fixed frame. You know, anything fixed frame we call inertial, right? So this is inertial frame and this is actually like body moving frame. So now what you wanted, you want the information. What it is very simple, right? What is the orientation, or you can say the angle difference between xb to xi, that is one, and the point I and b in x and y. These are the things you wanted, right? So these are the three variables you want to describe. So this is what you call the generalized coordinate x, y, psi. But unfortunately, the body B, or you can say the mobile robot connected with wheels or connected with some input device, that inputs all actually like happening here. Due to that, what you can see that the body will get an instantaneous velocity at each instant frame with something. What that means? The instantaneously it would be having a longitudinal velocity, lateral velocity, and angular velocity with respect to the body frame. Again, I'm saying it's instantaneous. So when you freeze the frame, you can see that there is an instantaneous velocity exists. So now you can see that you already studied what is robot kinematics. It is mapping between two spaces. So here, what are the spaces? You have x, y, psi. That is actually like with respect to initial frame, I call that is set of variable. That is what I call earth fixed space. Okay. Whereas, so UVR as another set of variable, in fact, it is one dimensional extra because it is a derivative of that, that would be in the body fixed frame. Now you need to map these two. So what you can do the mapping? So either you have to bring it down UVR into a positional domain, or you can say integrate that. Or what you can do, you can actually like elevate x, y, psi as the time derivative of generalized coordinate. So what is the easiest one? The easiest one is actually like bringing up x, y, psi as x dot, y dot, and psi dot. Why it is so? Because the UVR is the instantaneous velocity. You cannot make instantaneous position because the B position would be realized that the B is actually like the same, right? You will always see 0, 0, 0. That is nothing going to come. So in that sense, what you can do, you can actually like elevate the x, y, psi as x dot, y dot, psi dot. So now what I can do, if I want to elevate the x dot, I need to see what would be equivalent, because the body frame and the initial frame would be having an equivalent, right? So the UVR would be consisting, or component will bring some velocity to the x, y, psi. So in the sense, what you can do, you can take the individual velocity UVR, I can project it on I-frame. I see that what is the resultant vector on x-axis, y-axis, that would be equivalent to x dot, y dot. And what would be the angular velocity projection on z-axis, that would be the resultant velocity in z-axis. In this case, psi dot is straight away r. Why? Because the zi and zb are actually like parallel. Okay, so in the sense, what you have to project, you have to project u and v to I frame. I am taking u and projecting in I frame. So the x-axis will come u cos psi, and y-axis it will come u sin psi. So similarly, I am taking v vector and projecting into yi, that would be v cos psi, and projecting into, you can say, xi, that would be v sin psi. Now what would be x dot? X dot would be the, you can say, vector addition of u cos psi and v sin psi. Okay, that is what equivalent to x dot. Similarly, the vector addition of u sin psi and v cos psi would be y dot, right? So now you got it. Already you know, like psi dot is r, and you got it x dot and y dot. So you can rewrite this into a straightforward relations. Okay, so x dot I am writing into u cos psi minus v sin psi. Y dot is actually like u sin psi plus v cos psi, and psi dot is r. So now what you got it, you got the relation, but the relation in a differential domain, in the sense it is in a velocity domain. So what this equivalent? This is equivalent to forward differential kinematics, but that is not the interest here. What the interest here is, can I actually like make it two different spaces explicitly visible? So x dot, y dot, psi dot is already explicitly visible. Can I make it u, v, r explicit? Yes, I can do. So that if I do it, so what this is the mapping matrix. It is mapping the body fixed velocity command. We call it is velocity input velocity command. Okay, this is actually like time derivative of generalized coordinate. It is mapping the input commands to the generalized velocity coordinate. So this mapping matrix happening in a velocity domain, this is what we call Jacobian matrix. It looked like a rotation matrix, it is not. Please make it sure this is not the rotation matrix. It's a Jacobian matrix. Okay. So this is what we explicitly got it. So this equation, what we call kinematic model of a land-based mobile robot. Okay. So this is what we are actually like talking. What relationship it is giving? The relationship giving as velocity input command we call body fixed instantaneous velocity. That is giving a relationship between the derivative of generalized coordinate. So here you can see that this is function of psi, that you have to make it clear. So now this J is a Jacobian matrix. So you know what is Jacobian matrix. And fortunate, this is actually like a simple orthogonal matrix. So the J inverse is actually like simple J transpose. Okay. But if you take it in a very serious way, so for a given velocity command, indirectly you take a vehicle and connect the wheel and connect the motor speed. So what you will get? You will get velocity command, right? So in the sense what you have, you take the vehicle and give the velocity input command. What you are trying to see, you are trying to see how the vehicle move. So which is what we call forward differential kinematics, finding the derivative and take the integral and then see where the position all go. So this is what we call simulating the system, or you can say analyzing the system in the real. Okay. So this is what we call in a velocity level, simulating or analyzing. Similarly, you take the other side where the inverse, in the sense you are actually looking at something like a desired manner. So this is what your position trajectory with the time. Trajectory means time dependent, right? So you can actually like see how it goes. So then you are trying to find out what velocity if I give into a vehicle body, I can actually like attain. Indirectly, you can see like you are trying to control the system. Okay. But it is not directly you can call a control, but certain extent you can call, because it's an open loop control, or you call feed forward control. Okay. In velocity level. So now this is what you call the kinematic system. But this is a generalized, right? You did not bring it anything, your wheel or thruster or anything else so far. So for understanding that, we will take it to the next slide. So what the next slide is actually like one important aspect. So we will bring the degree of maneuverability. What that means? So the number of controllable input, right? So for that we are talking about wheeled mobile robot, then you have to talk about what kind of wheels you have, right? Based on the wheel, your degree of maneuverability will change. So for that, we are actually like talking about this, we have already seen. Okay. So these all we have seen. We are talking about degree of maneuverability. So the degree of maneuverability, very explicitly I said the number of controllable input, but the theoretical definition is sum of degree of mobility and steerability. What that means? Your body fixed velocity is directly controllable with certain input, that you call degree of mobility, whereas that is indirectly controllable. For example, you have vertical axis that is moving your velocity component, then you call that is steerability. Okay, so that is what we are actually like calling. So now if you look at that, the sum of degree of mobility and steerability, what you call degree of maneuverability. So which we already seen, it is simply number of controllable input. So this number of controllable input is actually like dependent on the kinematic configuration and actuator arrangement. Okay. So now the degree of maneuverability and degree of, you can say, freedom, there is some matching. So what that matching we will see here. Okay. So this is what we have seen in a mathematical form. So now we can see like this is what the derivation we derived. Now the zeta is actually like further decomposed with the, you can say, actuator space. Earlier you have seen body space to the inertial frame, body frame to inertial frame. Now you take to the vehicle, you can say wheel frame to, you call inertial frame. So there what you can bring it, the zeta I can write in terms of angular velocity of individual wheel. Then I need to map, then there would be a bigger matrix will come. That bigger matrix what we call wheel configuration matrix. Okay. So this is what we are trying to understand in the next slide. So for understanding that, first we will talk about the types of wheel. So broadly we'll talk about the wheel into two broad classification. So one is solid wheel, the other one is inflated wheel. Inflated wheel means so air filled or some inflated wheel, in the sense pneumatic filled. So the nitrate fixed or probably something like a liquid fill. So many combinations are come. That is inflated. The inflated wheel, you know, like why we are using. There are several, you can say, advantage. One important advantage is actually like it will absorb the shock and it will actually like give some flexibility to the suspension system. Okay. But we talk about the solid wheel. The solid wheel will have a two type. One is conventional wheel. The other one is non-conventional. Even in the conventional wheel, we have two sub-classification. So one is fixed wheel. The other one is rotatable or steerable wheel. Simply we call caster wheel or swivel caster. So the other side, non-conventional wheel, you can see like, so there would be a roller, passive roller fixed. So based on the location of passive roller, you call omnidirectional wheel or magnum wheel. Okay. So now we'll come back to the conventional wheel. Why it is called conventional wheel? The conventional wheel would be having a pure roll, in the sense we have a lateral slip is 0, in the sense, so lateral resistance is infinite theoretically. So for example, you take a car, you want to push it in a lateral direction, it is almost like impossible, right? Why? You have infinite resistance happen on the fixed wheel. So that is the concept. So you don't have a lateral slip, then you call that is a conventional wheel. But you want to intentionally do the lateral slip, then you have a passive roller. So this is what we call Swadesh wheel, because the Swadesh company has actually like brought it directly, Switzerland brought it. So that's why it is called Swadesh wheel. But the Swadesh wheel further classified into omnidirectional wheel and magnum wheel. So magnum wheel usually have 45-degree angle. So I did not see like the magnum angle is actually like varying, you can say 45-degree. Usually it has a 45-degree inclination, passive rollers. Okay. So these are the, you can say, type of wheel. So based on the type of wheel, we can actually like make the marking. So you can see these are fixed wheel. So if it is a green, it is a powered, or red is powered. I think I consider red as powered. This is non-powered. And this is actually like rotatable wheels. Okay, it's a caster. And if it is a simple, you call spherical wheel, then that is also considered as a caster. And this is omni wheel, this is a magnum wheel. Okay, so now you can actually like go across. So you want to understand what is the degree of maneuverability here. So you can see like this is having a power. This will give degree of mobility 1 and degree of mobility 2. And there is no steerable wheel, powered steerable. So in the sense, you can see like degree of mobility is 2, degree of steerability is 0, and then degree of maneuverability is 2. Right? So similarly, you can see here. So here you can see it's a power, degree of mobility is 1 and degree of steerability is 1. So you can see 1 plus 1 equal to 2. Right? So similarly here you can see it is all 3. The passive roller, although there, but there is no steerability exists. So in the sense here 3 mobility is there, but no steerability. Similarly here there are 4 steerability, 4 mobility is there, but there is no steerability. So here you can see 2 steerability and 2 mobility, which is actually like again 4. And these are actually like other way of convention. Okay. So with that, what you can actually like look at it. So you know now what is degree of freedom, what is kinematic model, and what is degree of maneuverability, right? So now you got one, you can say, itching point. What itching point? How I can actually like find the matrix W. So for that, there are several, you can say, method. I'll be proposing one of the method which is easiest. Okay. So it is not like that you need to know only this method, but this method is applicable to any system. You can say any wheel configuration. Whereas if you take the instantaneous center method, it is very difficult to find the instantaneous center for further configuration. For example, magnum wheel or omnidirectional, or you can say independent steerable wheel. It is very, very difficult. Whereas this particular generalized wheel model, it's very easy. So what we will do that, I hope I can actually like cover it. So is there a time exist? You have time, right? Because it required at least 20 minutes. If you have a time, then we can actually like see it. Otherwise, we can continue into the next session. Am I audible? Because pin drop silence.
Yes, sir. Yes, sir.
Okay.
Audible.
Okay. Then I will continue here because I think your break is 10:15 or 10:30.
It's 10:30.
Okay. Then I will attempt this. So we are actually like taking this generalized wheel model. For that, I'm taking a very complex wheel configuration where there are 4 magnum wheel. The magnum wheel, I already said it is supposed to be 45 degree, but it's look like not 45 degree. So what you can actually see that here there are 4 wheels which has a passive roller. I need to derive the W matrix for this whole configuration. So what W matrix means? It is actually like going to map between zeta to omega. So omega is actually like vector of angular velocity. Zeta is actually like input velocity command. The W is what you call wheel configuration matrix. So this is what I wanted. So for that, what I'm trying to take, I'm skipping everything. I'm taking one wheel at a time. Okay. So now you can see this is the body and this is what the wheel configuration. So now I'm taking this wheel alone as a case. So now this wheel would be having, if there is no roller, what it will generate as a drive velocity, which would be a tangential velocity. And we assume that there is no, you can say lateral slip, it is pure rolling. Then what happened? This would be having a V drive. Okay, that would be equivalent to R omega. Here R would be the radius and omega is the angular velocity. Since I used R as the angular velocity of the overall vehicle with respect to body frame, I'm taking A as the radius. Okay, so V drive would be A omega. So now I'm introducing the passive roller. You assume that the passive roller is rotating something like you call beta dot as the angular velocity. What would be the V slide? The V slide can actually like slide this direction or this direction, but this is actually like attached on the bottom of the wheel. So in that sense, it would try to slip in the other direction. For example, you take a duster and you put a chalk, roller chalk, proper cylinders, you put it and you just try to push it. What happened? The duster will not go straight. Because of the passive roller, it will go inclined way based on the direction which you kept it, right? So the similar direction, so what happened? You have a slide velocity. So now if you look at an individual wheel with a passive roller, there would be 2 velocities will come. One is V drive, the other one is V slide. But what one can understand, the V slide is not direct velocity because it is not given from anyone. It is a passive velocity which is generated due to V drive. If there is no V drive, there is no passive velocity. If the vehicle is not moving at all, there is no V slide at all, right? So in that case, the V slide, I can get a relation between V drive itself. So that is what my motive here. So for that, what I'm trying to take, this point, what you call, this is my centroid of the wheel that I'm calling C. And this is ith wheel, I'm calling Ci. So now what I'm putting, I already told I'm using a Cartesian coordinate system, right? So I'm bringing xci and yci as the axis. Now along xci, what I have, V drive. So that would be equivalent to omega I and ai, you know, right? So now I'm actually like writing as a V slide, that would be some phi angle. So that would be actually like having beta dot as the angular velocity of the passive roller and rho I is the radius of the passive roller. So this is what the velocity. So now I want to relate this beta dot rho I in terms of omega ai so that I can make it. But I cannot do that directly, right? What I can do, I can see xci dot and yci dot. What is yci dot? Yci dot would be having this component on the y direction. Okay. What is xci dot? The vector addition of this component and this component on the x-axis, right? So that is what I'm trying to do. So for that, I'm bringing phi I, positive rotation. Okay. Here actually like zi is actually like coming outward. I'm taking the angle between yci to the slide, or in the other way around, you can take the, you can say roller axis with respect to xci. Okay. So I'll just show you here. So this is the roller axis, right? So roller axis to the xci, or you can see the yci to the V slide. Both are same, right? So that is what we are actually like taking as a phi I. So if that is the case, what you can see, the V slide x-axis component comes like this, y-axis component like this. So y-axis component, yci dot is having only this component. So there is a phi I, say rho I is missing. Please correct it. So now you can actually like see it here. So this would be a vector addition, that would be xci dot, right? So yci dot I can rewrite in this way. So where rho I and beta dot I I can write as this way. And xci dot is actually like in this form. I can substitute this into here. So what I will get, xci dot and yci dot and omega ai would be in single form. So I rewrite and I write everything in omega I aspect. So what I will get one relation. So what I achieved one of the simplest way. I achieved the xci dot and yci dot if I know, and phi I is actually like based on the configuration, I can find omega I. So similarly, I can find omega I where I equal to 1 to 4 in this case. I'll get a relation, right? But can I actually get it xci dot and yci dot in terms of UVR? Yes, I can do. How? That we will see here. This relation I got it from here. I'm interested to find the relation between xci dot and yci dot in terms of UVR. For that, what I need to bring? So I need to bring the body. Okay. So the body is actually like the overall vehicle. So the CI is part of the body. You all agree, right? Because the wheel cannot go separate, right? It is attached with the body. So in that case, B and C are actually like inherent in a single body, but the B is having an instantaneous velocity UVR, right? So that we have to actually get it. Before that, I'm writing XB and XCI are having an angle difference that I'm calling as theta BI. So based on that, what I can write, the VCI with respect to B frame, I can write, right? So that is one step. The second step, what I can do, the velocity component along XB, I can write. That would be XCI dot cos theta BI. Indirectly, I'm actually like making it projection. XCI dot, I'm projecting into B frame. YCI dot, I'm projecting into B frame. And I'm seeing that what is along with XB, what is along with YB. That is what I'm writing it. So if I'm writing it, what happened? This would give one relation, right? This is what happening here. So this relation, I got it, right? Further, what I'm bringing it to UVR, and based on that, I'm transferring that into CI point. Okay. So what I can do, I can see that this is distance apart and angle apart. So I'm actually like getting this. So because it is a single body, whatever longitudinal velocity that would be coming. In addition to that, this is actually like R. So what you will get a tangential velocity which is connected and perpendicular to that. That would be having two component, which is I can write as a X direction and Y direction, right? So now if you look at it, at CI point, you have written the XCI dot and YCI dot one relation. So which you have written here, right? Similarly, I can write the same thing in terms of UVR, right? So this is actually like equal, right? This is supposed to be equal. Then what you got it? You got one relation between UVR to XCI dot and YCI dot, right? So this is what you got it. Now these two are equal. So now what you got a clarity, you already know omega I in terms of XCI dot and YCI dot. And now this XCI dot YCI dot I replace with what you call UVR, right? So now you have done, right? So what you have done omega I in terms of UVR. Now n number of wheel, you add it and you rewrite that, right? So further you want to make it in an initial frame, you bring it x dot, y dot and psi dot in terms of UVR. Now you rephrase this UVR what you have used here in terms of x dot, y dot and psi dot. Okay. So now what you have a relation, between your body fixed, you can see velocity to the angular velocity of the individual wheel, or initial fixed what you call time derivative of generalized coordinate to the individual wheel angular velocity. If you want to make it further, what you can do, you can find based on the wheel configuration, you can find omega 1 to omega n and you rewrite that into one side and you can recall this is one side UVR and you invert it. So now what that inverse of that matrix is nothing but W. For that I am taking one such example. I hope I did not open that file. Okay, so I'm taking such example. Okay, for example, in this case, it is a differential wheel drive. We all know like differential wheel drive, the U velocity would be the resultant of, you can say, to wheel velocity, and v velocity would be 0, and r would be difference into the distance between two wheels, that we already know. But now we will actually try to find the generalized wheel model base. So the dy1 and dy2, this is actually like positive direction of dy. So then this is d, and this is actually like minus d, that you got it. And the ci, c1 and c2 and b all are actually like in line with y. So in the sense the x coordinate would be 0. And I assume that both wheels are actually like same radius. And there is no passive roller, so you assume that phi1 and phi2 are 0. Okay. So in that case, this is what the overall picture. You calculate omega1 and omega2. That would be in the form of UVR. Since it's a fixed wheel and differential wheel, so there would not be any V. So this is what we rephrase it. So now you can write U and R. And now you actually like invert it. So that is what you call W. But the W is supposed to consist of V velocity also. So now this is what the W matrix, right? So similarly, you can actually like extend to n number of, you can say example, you can actually like substitute and you get it, right? So this is what the overall, even you can see the differential wheel, magnum wheel, all those things you got it. So this is what the overall picture. So I assume that you got it. Now you can see like this can be applied to any wheel configuration. It is actually like independent wheel drive or independent steerable wire or tricycle, or you can call you can say differential wheel or magnum wheel, omni wheel, anything you can use it. Even need not to be actually like you call same angle, 45 degree minus 45 and all. Even you take any angle, that will be still addressable. Similarly, you can see like it need not to be in same distance. Even you move it the distance, still it can be applicable. So that is what the overall idea. That's what the overall picture of this particular slide set. I hope now you got some clarity on what is kinematics. Okay, what is actually like overall kinematics and all. So the next session we will attempt what is kinematic control, and how we can actually like talk about one subclass is called holonomic and non-holonomic. What is holonomic and how you can define with respect to W. These all we will discuss. I open for the questions now. Okay, and probably. So I already like share the link, but if you are actually like interested, you can actually like go and register. It is actually like open for, you can say for you. So I'll just open that Swayam. So till you post the question or you can say ask the question, I'll just put it. I think, I hope the course is already online enabled, although it is start officially 18th, but the you can say few weeks lectures are already posted. Okay, this is the course link. Okay, so in addition to that, if you want to know more about manipulator, okay, so you can actually like use several lecture materials are available, but I also like have a posted one YouTube series, because this is actually like used to come in the next semester of NPTEL course, but I don't want to actually like keep it, so I keep it open. So this also like you can actually like find it. So this lecture series also available, so you can actually like find it. So more detail about mechanics and control of robotic manipulator would be discussed in this lecture series along with simulation. Similarly, this wheeled mobile robot also along with MATLAB simulation will be discussed. Okay, so these two you can actually like take it if anybody interested. So with that, I'm closing the first session with some questions.
Participants, you are free to ask questions if you have any doubt. Please. Thank you, sir.
Yeah. So 10:45 is the next session, right?
Yeah, sure.
Yeah.
So we have 10 more minutes for the discussion.
In IIT, we restrict 40 minutes, at least I restrict to 40 minutes, although the lecture hours is 50 minutes, because after 40 minutes, the listening capability will go. But here I was talking like more than 50 minutes continuous. It is really difficult.
Yes.
So there is no standard textbook, but if you wish, you can take Introduction to Autonomous Mobile Robots by Roland Siegward. You can actually like take it. So he works in ETH. I had a chance to work with this lab. So in fact, I got an offer in EPFL for a faculty position when I left Germany, but I came to IIT Palakkad just to make sure that my family is happy. So there is no standard textbook for at least mobile robots. Probably if you are really interested, you can take Modern Robotics by, you can say, Kevin Lynch. That book would give, you can say, screw algebraic based mechanics of manipulator. But so you would be talking one chapter on wheeled mobile robot. That would be more useful for the starting point. And for your kinematics and navigation side, the Roland Siegward book would be beneficial. And you want actually like what you call dynamics and control, you can take Introduction to Mobile Robot Control by Safastas. Spyros Safastas. He is actually a Greece professor or Italy professor. So you can take these three books are very useful. But none of the book will give a standard straightforward text. Okay, you have to dig and then trigger it. So that's why several of you can say faculty members suggest me to write a book, but I don't have enough time to write a book on wheeled mobile robots. I'm not actually like boasting myself, but this is a frank. If you even you trigger it, you go to research on the books, definitely you will not find the standard text which is available. Okay. So I hope you understood, because no questions means I always assume that nothing understood. But the other way around also, everything is understood also, like the other case. But I assume that the other way around. Okay. Because if somebody asks question, then only we can see how much reachability happened. I'm not talking about, yes.
Here, balancing.
Yes, Santhakumar.
Will this be balancing, regarding balancing will be discussed here in this course?
No, balancing will be in locomotion, right? So if you look at it, the balancing will be completely different. In fact, I skipped the slide set about the locomotion slide. I told, right? So I straight away came into lecture 3 and lecture 7. I skipped several because it is actually like one additional thing. The stability is actually like not a problem as long you talk about wheeled mobile robot. Until you do a two-wheel mobile robot, then only you would be bothering about stability. Otherwise, the stability is not a problem in wheeled. But if you are talking about legged robot, definitely you need to think about the stability. So there we talk about dynamic stability and static stability. So these all discussed in the lectures series in the SWAYA.
Okay. Okay, sir. Thank you.
Yeah.
Any more queries?
If not, then I will close it.
Okay.
My side. Yeah.
Yeah. Yes, sir. Now we can join at 10:45.
Sure. Thank you. Bye.
Okay.